In this lesson, we'll be going over each type of circuit. We'll first be covering series circuits, and then parallel circuits, and finally mixed circuits. So first off, let's start series circuits. Taking a look at this diagram, there are multiple components that we need to go over in order to understand series circuits. First, this component is called a battery. The strength of it depends on its voltage. This voltage supplies a current, which flows through the wires to power the resistors. A resistor is any electrical device that is hooked up to the circuit. So it can be a toaster, a blender, or a TV. The current is constantly being circulated throughout the circuit to power all the resistors. But let's say that there was a very weak battery hooked up to the circuit. The resistors attached to it will probably work at a very low efficiency, or may not even work at all. But what if we had the opposite problem, where the battery is way too powerful compared to the resistors? Say we hooked up a light bulb. What would probably happen is it would light up and then instantly burn out. But let's say that there was an equilibrium between the power of the voltage and the resistance of the devices, and that this resistor was a nightlight and this resistor was a microwave. Obviously, the microwave is a lot more complex, so it will put a lot more resistance on the circuit and require a lot more voltage to run compared to the nightlight. Now that we have a little bit of an understanding about series circuits, let's try and solve one. To do that, there will have to be a few given numbers. So let's say that the total voltage is 15 volts, and that these three resistors, R1, R2, and R3, each have respective resistances of 21 ohms, 28 ohms, and 32 ohms. With that information, we can now solve the rest of the circuit. But what variables are we looking for, and how do we solve for them? Well, obviously, there would be a total voltage, a total current, and a total resistance. Based on how many resistors are in the circuit, there's also a current and voltage for each resistor. We know what variables we are looking for, but now how do we solve for them? Well, let's take a look at some of these equations. The first one is Ohm's law. V equals I times R. Voltage equals the current multiplied by the resistance. This formula is universal, meaning it can be used in all three types of circuits, whether it's series, parallel, or mixed. However, there are a lot of formulas in which they are true for one type of circuit, but false for the other type. You see, where series circuits get their name is that all the resistors are all lined up in one continuous path, as they are in series with one another, where the current flows to. However, it's different for a parallel circuit, in which the current splits up and travels on multiple different paths. Anyways, let me introduce the Kirchhoff laws for series circuits. Those including that the current at one resistor is equal to the current at each of the resistors, which is also equal to the total current. Meaning that if we find one of the currents, we have found all of them. Another formula is that the total voltage is the sum of the voltage at each of the resistors. And finally, very similar to the last formula, the total resistance equals the sum of the resistances from all the resistors. What we can first do is solve for the total resistance, as we have R1, R2, and R3, and so RT equals 21 ohms plus 28 ohms plus 32 ohms to equal a total resistance of 81 ohms. Let's box it to keep it neat, and now plug it in for RT. Now, seeing as we have the total voltage as well as the total resistance, we can now solve for the total current using Ohm's law. And with some rearranging, the current equals the voltage divided by the resistance, which equals 0.19 amps, rounding to two significant digits. Just to clear up some confusion, for Ohm's law, you cannot use V1 and I2 to find R3. No, you must use two values in the same row to solve for the missing one. Now, remembering this formula, that each of the currents are equal to each other, that means that we can plug in 0.19 amps for each of the other currents. But to show our work, we need to show that IT equals I1 equals I2 equals I3, which equals 0.19 amps, to get full marks. Now look at that. We have all of the currents as well as all the resistances, and now we just need to find the three voltages. And so V1, V2, V3 each equals 0.19 amps times 21 ohms times 28 ohms times 32 ohms, which equal 4.0 volts, 5.3 volts, and 6.1 volts, rounding to two significant digits. These numbers are probably right, but there is a good way to confirm recalling this formula, and so Vt equals 4.0 volts plus 5.3 volts plus 6.1 volts, which equals 15 volts when we round to two significant digits. And now the circuit is completely solved, and we have showed all of our work. Next, we'll go over parallel circuits. The best way to learn about parallel circuits is to compare it with series circuits. A great way to explain this is, say you're going to the amusement park. When you arrive, you see that there's only one line. After you wait for your turn, you first go through the metal detector, then someone searches your bag, and then you show your ticket to prove that you paid for your trip. Doing this can be a long and tiring process and can steal some of your energy that you want to put to riding all the roller coasters. This analogy sums up series circuits, as there's always one singular path in which current is moving and constantly flowing through the wires in and out of the battery, while always having the constant strain of these three resistors. Now, you would agree that taking away a resistor would overall result in less resistance in the circuit, but what if instead we added one? Then this would increase resistance in the circuit, correct? Let's use that same analogy of the amusement park for a parallel circuit with three resistors. Let's say you come back the next day, but now instead of there being only one line, there are now three different lines where the park is inviting people in. And instead of having three individual stations, all three are packed into one. And so you would first walk through the metal detector, hand the worker your bag for him to look through it, and they'll be done by the time you're done showing your ticket. And so what this shows is that for a parallel circuit, the current is being spread out through multiple paths, and in each path, that current only has to suffer the resistance of one resistor rather than three. So now this begs the question, does adding more resistors increase or decrease resistance? As in series circuits, the more resistors that you add, the more that you're increasing the resistance. And quote-unquote logically speaking, for parallel circuits, adding more resistors should increase resistance. Not true. Let's say that the park had 300 people lined up outside, evenly distributing these people along the three paths. Each station would have to deal with 100 different people, checking their bags, checking their tickets, making sure they walk through the metal detectors, whatever. What would happen if we removed this third path? The park closed it down. Now dividing those 300 people, each line would now have 150 people, causing more resistance and a longer wait time. But what if we instead added a fourth resistor, or a fourth line to get into the park? Now dividing that 300 by 4, there would be 75 people in each line. Or if there were 5 lines, there would be 60 people in each line. And so that is definitive proof that for parallel circuits, adding more resistors decreases resistance. Now let's get into solving a parallel circuit. For our given values, let's say that the total voltage of the battery is 250 volts. The first resistor, R1, had a resistance of 160 ohms, R2 had a resistance of 210 ohms, and R3 had a resistance of 125 ohms. For our formulas, there is of course Ohm's law, in which the voltage equals the current multiplied by the resistance. And then in terms of the Kirchhoff laws for a parallel circuit, first, the total voltage is equal to the voltage at each resistor. Similar to the Kirchhoff law for current in a series circuit, if you have the current at the first resistor, for example, it would equal the same current for the total current and at the current at the rest of the resistors, which is exactly the same for voltage in a parallel circuit. And then for finding total resistance, the formula is the same as the series circuit formula. However, it is the sum of the reciprocal of all the resistances. For parallel circuits, when more resistors are added, the resistance actually decreases, and so it is guaranteed that the total resistance will be lower than the lowest resistance in the whole circuit. So for this one, it would be lower than 125 ohms. And then finally, the total current equals the sum of all the currents at each resistor. So let's say the current was coming out of the battery, and obviously because this was a parallel circuit, not a series circuit, all the current is distributed in the 3 different paths. At this point, all the current is together, but once it reaches these points, the current splits up and goes to each individual resistor until it comes back all together at about this point. And now we're on our own. However, I did make it a little bit easy, seeing as I already gave the total voltage, which according to this formula is equal to V1, V2, and V3, which we do have to show in order to say how we found it. Now for the resistances. Of course, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, which would be 1 over 160 ohms plus 1 over 210 ohms plus 1 over 125 ohms. Now the easiest way to do this is to just put it into your calculator. I always use brackets just to be safe. You should be getting 0.019 ohms, which equals 1 over RT. And now to find RT, we can simply just find the reciprocal, making it RT over 1, which is just RT. And of course, we would have to do the same to the other side. So it would be 0.019 over 1. And when we do the reciprocal, we can see that it's 1 over 0.019. And so rounding to 2 significant digits, we can find that the total resistance is 53 ohms, which we can fill out for RT. And now we have found all of the voltages as well as all the resistances. All that's left is to find the currents. And going back to Ohm's law, the current equals the voltage divided by the resistance. And so each of them are 250 volts divided by their respective resistances. And so 250 volts divided by 53 ohms equals 4.7 amps for the total current. And then doing the same for the rest. I1 is 1.6 amps, I2 is 1.2 amps, and I3 is 2.0 amps. Now obviously to confirm, we can add all of these up. 1.6 amps plus 1.2 amps plus 2 amps equals 4.8 amps, which is different from 4.7, but this 0.1 amp deviation is negligible as it is a result of rounding, but nevertheless confirms that we have done all the right work and have found the correct answers. And now finally, let's cover mixed circuits, which are also known as combination circuits, as they're a combination of both series and parallel circuits, meaning that we have to use every single one of Kirchhoff's laws as well as Ohm's law to solve them. Let's get right into our first mixed circuit. This one is pretty easy. As you can see, we are given the voltage of the battery as well as the resistances of each resistor. The first thing we should try to solve is the total resistance. To do that, we need to think outside of the box. Taking a look at this circuit, it looks like the first resistor is in series with these 2 resistors that are in parallel with each other. So in other words, we can say that R1 is in series with RA. And as we know, for a series circuit, total resistance equals the sum of all the resistances. So then how do we find RA? Well, we know that for solving resistance in a parallel circuit, it is the sum of the reciprocal of each resistance. So to solve for RA, it's 1 over RA equals 1 over 33 ohms plus 1 over 25 ohms. It should give you about 0.07 ohms, which equals 1 over RA. And then doing the reciprocal of both for 1 over 0.07, this gives us 14.2 ohms. And now to find RT, we add this 14.2 ohms to R1, which is 5 ohms. And rounding to 2 significant digits, we get 19 ohms for RT. Now that we have the total voltage as well as the total resistance, we can find the total current. And so IT equals 42 volts divided by 19 ohms, which equals 2.2 amps. Now, if you remember, for a series circuit, the total current equals the current at each resistor, but that's just for a series circuit. And if R1 is in series with RA,
then that means IT equals I1, which equals IA, which all equal 2.2 amps. Now we can find the voltage at the first resistor. So V1 equals 2.2 amps times 5 ohms, giving us 11 volts. And since we know that in series circuits, the total voltage is equal to the sum of the voltage at each resistor, and that in a parallel circuit, the voltage is equal for both resistors. So following the path, R1 would first use up 11 volts, leaving the rest for R2 and R3. And so to show our work, we would put that V2 equals V3 equals the total voltage minus the voltage at the first resistor, which is 31 volts. And we can fill that in for V2 and V3. And now to find both of the currents of the two parallel resistors, we can do I2 equals 31 volts divided by 33 ohms equals 0.94 amps, and I3 equals 31 volts divided by 25 ohms to equal 1.2 amps. Just to confirm, we can add this 0.94 to 1.2, and it's just short of 2.2, but we know that we got it right since IA should equal 2.2. Let's move on to another one. Let's make it a bit harder too. Here we are given 4 resistors as well as the total current. When we look at the path of the circuit, we can see that it's first R1 and R2 in parallel with each other, which here again we can label as RA, as RA is in series with R3 and R4. Similar to the last question, we can solve for the total resistance. So first, solving for RA, 1 over RA equals 1 over 14 ohms plus 1 over 39 ohms. You should get 0.097 ohms equals 1 over RA. Taking the reciprocal of each, RA should equal 10.3 ohms. And to find RT, it equals 10.3 ohms plus 26 ohms plus 47 ohms to get a total of 83 ohms, rounding to 2 significant digits. The next thing that I wanted to point out is take a look how the current moves throughout the circuit. See, it first goes into this junction where there are these 2 resistors in parallel. The current splits up into each of these resistors, but then meets back over here to form 24 amps again. And as we know, in a series circuit, the total current is equal to the current at each of the resistors. So that means IT equals IA equals I3 equals I4, which is 24 amps. So we can plug this in for I3 and I4, and all we need to find is I1 and I2. Next, I see we have both IT and RT, so we can find the total voltage. So VT equals 24 amps times 83 ohms, and rounding to 2 significant digits, it would actually be 2000 volts. But the correct way to show it would be 2.0 times 10 to the power of 3 volts. But for you guys, I'll write it as 2000 volts. Now next, a common mistake that a lot of people would make is they would think, oh, the wire's going to these parallel resistors, and according to voltage in a parallel circuit, they equal the voltage going in, no? So it should be 2000? Wrong. Because you're forgetting that R1 and R2, or RA, is in series with R3 and R4. So everything added up has 2000, not just VA for voltage. Meaning, the voltage for V1 and V2 should really be 2000 minus the voltage at R3 minus the voltage at R4. So first we'd actually have to find V3 and V4. Luckily we have both I3, I4 as well as R3 and R4. So V3 equals 24 amps times 26 ohms. That rounds to 620 volts. And V4 equals 24 amps times 47 ohms, which rounds to 1100 volts. So now, the total voltage minus V3 minus V4 equals VA, or V1 and V2, which equals 280 volts. And now finally we can figure out I1 and I2, which when added up together should be close to 24 amps. So I1 equals 280 volts times 14 ohms to give us 20 point amps. That's a good way to make it so that it has two significant digits and not just one by adding that decimal at the end. And then for I2, 280 volts divided by 39 ohms equals 7.2 amps. Now in total that's 27 amps, but we know that there was a bunch of rounding going on due to significant digits, but we know that we did everything right, and nothing seems to be abnormally wrong, so I'd say we're good on this one. Now let's go into the hardest of them all. Okay, let's analyze this. Once again, we are given the voltage as well as a total of 6 resistances. Taking a closer look, it looks like R2 and R3 are in parallel with each other, so we can label this RA. And it looks like also R4 and R5 are parallel, so we can label this RB. But what we can also notice is that RA and RB are parallel with each other, so we can call this RC. And now we can also see that R1 is in series with RC as well as R6. The hardest part of trying to solve a mixed circuit is trying to figure out the plan, figure out how you're going to execute it. Next, you always have to stay consistent with all of your calculations while also using every single rule to your advantage. So first, to solve for RA, we can do 1 over RA equals 1 over 21 ohms plus 1 over 46 ohms, which should equal 0.069 ohms equals 1 over RA. Then if we just find the reciprocal, RA should equal 14.4 ohms. Now for RB, 1 over RB equals 1 over 18 plus 1 over 16. We should get 0.118 ohms equals 1 over RB. And then doing the reciprocal, we should get 8.47 ohms. And now since RA and RB are parallel with each other, 1 over RC equals 1 over 14.4 ohms, which is RA, plus 1 over 8.47 ohms, which is RB. This should give us about 0.1875 ohms, which equals 1 over RC, and then we can do the reciprocal to find 5.3 ohms, and then finally to find RT, we add 5.3 ohms plus 15 ohms to get 55 ohms for our total resistance. And now I wasn't kidding about this one being hard, and there's still so much to find. Luckily, we have the total voltage as well as now the total resistance, so we can find the total current. IT equals 150 volts divided by 55 ohms equals 2.7 amps. And looking at the circuit as if we're a series, IT should equal I1, which equals IC, which equals I6, which equals 2.7 amps. So we can fill that in for I1 and I6, but we still have to calculate each individual current for the 4 resistors in IC. Now that we have I1, I6, as well as R1 and R6, we can find V1 and V6. So V1 equals 2.7 amps times 15 ohms equals 41 volts, and V6 equals 2.7 amps times 35 ohms equals 95 volts. And similar to last question, we can subtract the two voltages for the resistors that are in series from the total voltage to find the voltages of all of the resistors that are in parallel, in which they all have equal voltage. And so to show this, we would put Vt minus V1 minus V6 equals Vc, which equals Va, which equals Vb, which equals V2, V3, V4, and V5 to equal 14 volts. And now all we have left is I2, 3, 4, and 5. And so I2 equals 14 volts divided by 21 ohms equals 0.67 amps. I3 equals 14 volts divided by 46 ohms equals 0.30 amps. I4 equals 14 volts divided by 18 ohms equals 0.78 amps. and I5 equals 14 volts divided by 16 ohms equals 0.88 amps. Now just to confirm, we can add them up, and it equals just under 2.7 amps, so we know that we did everything correctly. There's never a circuit that's unsolvable. You can always use what you were given to find for the unknown values, whether you use Ohm's law or any of the Kirchhoff's laws. Just make sure you use the correct significant digits, take everything one step at a time, and confirm that all of your work makes sense and adds up correctly. If you've made it this far into the video, chances are you're learning a lot and enjoy the content. So if you don't mind, consider subscribing, as it shows me that you like what you see, which helps me post more videos. Anyways, that's all for now. I hope you have a wonderful day.